Welcome back to the deep dive. Today we're going into a result that was, well, it was so small, but so huge, it basically forced the quantum world to tear up its own rulebook.
We're talking about the late 1940s. Picture a quiet lab at Columbia University.
Right. And inside, Willis Lamb Jr. is running this incredibly precise experiment on hydrogen, the simplest atom there is.
And he's looking at an energy reading that, according to all the beautiful established physics, just shouldn't exist. It was a ghost in the machine.
And that beautiful physics was Dirac's relativistic quantum theory. I mean, this was the gold standard.
It was. And it made a very, very clear prediction about hydrogen's energy levels. Two of them in particular, the 2s1/2 and the 2p1/2, should be perfectly degenerate.
Which means they have the exact same energy. Zero difference.
Exactly. They're supposed to be quantum twins. If you drew them on a chart, the lines would sit right on top of each other, perfectly overlapping.
But Lamb's experiment, what we now call the Lamb shift, found this tiny offset. It proved the perfect equations were, well, wrong, or at least incomplete.
And that tiny little gap was the first piece of really hard lab evidence that the vacuum, the empty space between things isn't empty at all.
So that's our mission for this deep dive. We want to understand this shift, how Lamb found it, how mainstream physics explains it, but also how we can look at it through the lens of motion theory.
Right, because from a motion theory perspective, Lamb's result wasn't some strange anomaly. It was almost inevitable. It was the proof that the vacuum isn't just the stage for the play. It's one of the actors.
Let's start with that perfect world, the clean hydrogen fantasy that Lamb's work really just shattered.
The clean fantasy. This is a simple picture, right? A proton sits in the middle, an electron orbits it. For years, physicists saw this as a neat, tidy two-body problem.
Schrödinger solved it, then Dirac came along and made it relativistic, more precise.
And Dirac's math, with all its inherent symmetries, absolutely demanded that the 2s and 2p states have identical energy. It had to be that way.
So if we translate that into the language of motion theory, what's the core assumption being made there?
The assumption is that the electron's motion pattern only feels the pole, the motion gradient of the proton. And crucially, that the background all around it is completely silent, utterly passive.
And the really tricky part is that for most things, that assumption works incredibly well.
Oh, it works beautifully for basic chemistry, high school physics. But it completely falls apart the second you start pushing for Mennekertz-level accuracy, which is exactly what Lamb was doing.
So his genius wasn't in coming up with a new theory. It was in asking this really annoying, really precise question.
Yeah, basically, are we absolutely sure they're the same? Or have we just not listened carefully enough?
Okay, so how did he listen? What was the method?
He used something called microwave spectroscopy. He created a beam of hydrogen atoms and fired it through his apparatus.
But how do you measure a difference between two states that, again, are supposed to be the same?
Well, that's the clever part. He prepared the hydrogen atoms so they were in what's called a metastable 2s state.
Metastable meaning it's excited, but it doesn't decay right away. It's stable enough to be studied.
Exactly. It gives him a target to work with. Then he zapped these atoms with very finely tuned microwaves. The goal was to see if he could nudge them from that 2s state into the 2p state.
And if the energy difference was zero?
He'd need a microwave frequency of 0, which is, nothing. But he was looking for a non-zero frequency. He was hunting for a resonance.
How did he know when he found it? How did he see a transition happen?
By using a small electric field. See, the 2p state is incredibly unstable. As soon as an atom jumps to 2p, it almost instantly decays and spits out a flash of light.
So the light is the signal? More light means more atoms made the jump.
Precisely. He just had to sweep the microwave frequency and watch for the point where the light was brightest. That frequency would correspond exactly to the hidden energy difference.
And the number he found wasn't zero, it was about 1,000 megahertz.
1,000 megahertz. I mean, that's a tiny amount of energy, but conceptually, it was the sledgehammer. It proved the 2s orbital is actually at a slightly higher energy than the 2p.
It meant there was some kind of energy correction happening that the beautiful Dirac theory had completely missed.
And it sent everyone scrambling. It really forced theorists to ask, okay, what else is out there? What is the electron interacting with that we've just been ignoring?
And that scramble is what led to QED, quantum electrodynamics.
The most precise, most tested theory in all of science. All because of that 1,000 megahertz anomaly.
Let's get into that QED explanation. The math is famously brutal, renormalization, Feynman diagrams, it's a mess.
Yeah.
But what's the physical story? Why is 2s shifted up?
The story is actually pretty intuitive, and it comes down to two main effects. The first is called self-energy.
Right, the idea that the electron is sort of wearing a fuzzy coat of virtual particles.
That's a great way to put it. The electron is constantly emitting and then reabsorbing virtual photons. It's interacting with its own field. This jitter, this cloud of activity, effectively smears the electron out a little bit and nudges its energy level up.
Okay, but if all electrons do that, why would the 2s and 2p states shift differently? That's the key, right?
That is the key. And that brings us to the second and more important effect, vacuum polarization.
The idea that empty space isn't empty.
Far from it. The vacuum around the proton is seething with these virtual electron-positron pairs that pop into existence for a split second and then disappear.
And these pairs can affect the proton's charge.
They do. The virtual positrons are attracted to the proton and the virtual electrons are repelled, so you get this tiny little polarized shield around the proton's core. It screens its charge.
Ah, okay. So the orbiting electron doesn't feel the full, raw charge of the proton. It feels a slightly dampened version.
Exactly. But, and here's the punchline, it depends on where the electron is. The 2p orbital is shaped like a donut. It has zero probability of ever being at the nucleus.
It stays away from the center.
Right. But the 2s orbital is a sphere. It has a small but non-zero chance of being found right at the proton's core.
So the 2s electron actually spends a little bit of time inside that screening cloud.
Yes. It gets closer to the bare, unscreened charge of the proton. Because it penetrates that cloud, it feels a slightly stronger attraction on average than the 2p electron does. That tiny difference in how they experience the vacuum polarization is what creates the 1000 megahertz energy gap. It's the Lamb shift.
That is incredibly subtle. The shape of the orbit determines how much it interacts with the vacuum's noise. Okay, let's pivot. Let's look at this same phenomenon, but through the motion theory framework. We're moving from particles and virtual clouds to what?
We're moving to talking about stabilized motion knots that are embedded in a restless sea of motion.
You're going to have to define motion knot for us.
A motion knot is just what we call an electron. It's not a point, it's a stable, organized, self-sustaining pattern of motion. Its structure is what gives it properties like mass and charge.
And the restless sea.
That's the vacuum. It's the background state, full of low energy, unsynchronized jitter. It's not nothing, it's just incoherent motion.
So in this language, what is the Lamb shift? It's not about virtual particles anymore.
No. The Lamb shift is simply the measurable proof that different orbital patterns, different shapes of motion, have different amounts of exposure to that noisy background. The 2s pattern, because of its shape, just sits a little bit closer to the noisy, jittery sea than the 2p pattern does.
And that interaction with the sea retunes its energy slightly.
It retunes it. And motion theory uses two concepts to keep track of this, S and R.
Okay, what are S and R?
S is for synchronization density. Think of it as a measure of how organized and coherent the motion is. S is very high, right near the proton, where things are tightly structured. It drops off as you move away.
And R?
R is for leak, or decoherence. It measures how quickly that organized motion frays and dissolves back into the random background. The deep vacuum is a high R, low S environment. It's pure noise.
So the Lamb shift becomes a bookkeeping problem?
A synchronization bookkeeping problem, yes. The 2s and 2p patterns have different spatial profiles. They overlap at the low S, high R vacuum regions differently.
The 2s pattern, because it gets closer to the nucleus, has a different kind of interaction with that noisy boundary.
It experiences a different amount of motion leak than the 2p pattern. And that leak has an energy cost. That cost is the 1000 megahertz shift. We're just measuring the price an organized pattern has to pay for existing in a noisy universe.
I have to push back here a bit. QED, for all its mathematical difficulty, can calculate that 1000 megahertz number with incredible precision. Does motion theory's framework, this S and R bookkeeping, does it actually make the calculation easier? Or is it just a different language for the same complex math?
That's the million-dollar question, isn't it? And it's the right one to ask. A new concept is only useful if it leads to a new or better calculation. The ultimate goal of motion theory isn't just to redescribe it, it's to reproduce that number by mapping the S and R gradients. The ambition is that it should provide a more direct mathematical path. But look, the universe is what it is. That 1000 megahertz number is a hard target, and any theory, no matter how elegant, has to hit it.
The experiment is always the final judge.
Always. Lamb didn't win with a beautiful idea. He won with a brutal, undeniable measurement.
Let's talk about that legacy. Because this measurement, in a way, it killed the dream of perfect symmetry in physics.
It really did. It killed that wishful thinking. There's this hope that the deep rules of the universe will be perfectly clean, perfectly symmetrical. Lamb showed that even in the simplest atom you can imagine, the background noise of the universe gets a vote.
The symmetry is only there if you pretend the background is silent.
Which it isn't. So the symmetry is, in a way, fake. And that lesson scales up to everything. Any theory that treats the background space-time, the vacuum, whatever, as a passive stage is missing half the picture.
And of course, this work directly kicked off the development of QED.
It gave Feynman, Schwinger, and Tomonaga the problem they needed to solve. And they did. They developed the tools to calculate things like the electron's magnetic moment to a ridiculous number of decimal places, matching experiments perfectly.
It was a total paradigm shift. We went from thinking about billiard balls in empty space to
thinking about patterns of motion embedded in a restless medium, where you have to account for the background. The corrections aren't optional, they're fundamental.
So what does this mean for any future theory? What constraints does Lamb's legacy place on something like motion theory?
It sets up four really non-negotiable hurdles. First, and most obviously, you have to be able to calculate the 1,000 megahertz shift. If you can't get the number right, you're not playing the game.
That's the entry fee. What's second?
Second, the vacuum can't just be a pretty idea. Its properties, in our language, the S and R values, have to be real physical parameters. They have to be knobs you can turn in the math that measurably move the spectral lines.
Okay.
Third, coherence length matters. The theory has to explain why the 2s and 2p orbitals are different. It has to show, from their geometry, why one is more affected by the vacuum noise than the other.
And the final constraint?
The standard of proof. Precision experiments are the only judges that matter. A new theory has to be willing to be tested with the same brutal accuracy that Lamb used to change the world. Elegance is nice, but the numbers have to work.
When you look back, it feels like Willis Lamb was the one who just put his ear to the universe and heard something everyone else was filtering out as static. He heard the vacuum breathe.
He did. He caught the universe red-handed, retuning its own laws in real time. He proved that the noise isn't a mistake in the measurement. It's a fundamental feature of reality.
That tiny shift, the 1,000 megahertz, it's a profound statement about how interconnected everything is.
It is. I think the best way to think about it is this. The Lamb shift is the invoice. It's the bill you get for pretending the background was free.
The invoice for pretending the background was free. That's a powerful way to end it.
It's a reminder, no pattern, whether it's an electron, a star, or an idea, ever exists alone. Every single thing is constantly in conversation with the sea of motion it's floating in. And that conversation always has a measurable cost.